Hi, welcome to Ordinary Differential Equations. Today's topic will be initial value problems. So we are going to talk about initial conditions, various type of initial value problem, and interval of validity. Going to look at several examples related to these. And two advanced topics are going to be postponed. One is existence and uniqueness of solutions, and the other one is boundary value problems, or BVPs. Okay, let's see what is meant by initial value problem. Well, probably you have played football or watched somebody else play football, and one of the main things that happens in the game is that somebody throws a ball. Well, the moment at which you throw the ball, that one we might refer to it as T0. That's the beginning of the ball going up in the air. At that moment, let's imagine the game is being played in 2 dimensions. There is some point at which you decide to throw the ball. So let's refer to this as x0, y0. So that would be some sort of initial position. Then you decide to throw this ball at a certain angle and a certain speed. So you have something, perhaps you can call it the initial velocity. So we have initial position. Of course, there's a initial velocity, and then of course there is an initial time. Well, physical processes that we are going to study this semester are kind of like throwing a ball. Some sort of experiment is going to happen, and something is going to go on. It's like the effect of gravitation on the ball in the air. But any of these events starts at a certain state. That initial state is going to be referred to as initial condition. So initial condition is how a certain experiment is set to start. Now, mathematically, how does this thing is going to show itself? Let's first start with the first order equation. You remember what was first order, meaning like if your independent variable was x and your dependent was y, then all that you have added to the fray is just y prime. So first order is a story that's a mix of these cast of characters. Let's just make up something just so that it doesn't look too abstract. Suppose you have a 2y prime plus xy is equal to, say, cosine of x. Any formula with x and y prime is going to be a first order ordinary differential equation. Okay, that's like saying there is a certain ball in the air. The equation is saying something is tumbling up in the air. But how did this whole thing start? How did this thing start? So that is, for example, for these things, we have to set the starting value of x and the corresponding starting value of y. So I might say x at the beginning was 2 and y at the beginning was, say, 5. The way we capture this thing is by saying y of 2 is 5. At the start, x being 2, y is 5. That's what it means. Well, in general, we could have any kind of a relationship between x and y y prime. So that generality is typically shown is f of x and y. So this thing just says the derivative is some given function of x and y. For example, here, if you wish, your derivative is minus xy plus cosine of x divided by 2. That's what your y prime is. Yeah, so in general setting, we assume that this is given. And then we are going to specify that y at some given x0 is some y0. So that is the first order initial value problem. First order initial value problem looks like that. Similarly, you can have a second order initial value problem. So in that case, you have y double prime added to the fray. There's x and y prime and y double prime. And y double prime is given to us in terms of the other ones, x and y prime. In that case, we have two initial conditions reminiscent of the situation here, that you have a position and a velocity. And the higher order the equation is, the more initial conditions you need to get it going. So in that case, we will have y of, for example, x0 is being some y0, and y prime of x0 is being some y prime 0. So this is a description of, so this was the first order initial value problem, and this is the second order initial value problem. Excuse me. That is what is meant by initial value problem. We are going to talk briefly about boundary value problems toward the end, and I'm going to have some small examples related to that. There could be an entire books on that, but we probably not going to have enough time to look at it extensively. Let's look at some simple examples. Here is some example taken from your text. Here this says, in this problem, y is equal to 1 over 1 plus c1 exponential of minus x is a one parameter family of solutions of the first order differential equation y prime is equal to y minus y squared. So we have a differential equation, y prime is equal to y minus y squared, and we are already given a solution. Never mind where does that come from. That's going to be coming up in a couple of weeks, but right now we're just trying to get our feet wet with some basic ideas. Suppose there is this equation and somebody has already solved it for us. It says find a solution of the first order IVP consisting of this differential equation and the given initial condition. So an initial condition is specified. Y of 0 is equal to minus 1/4. And then the question is find the largest interval, additional things I'm adding to this, find the largest interval in which the solution is defined. So that is just to remind us of the issue of interval of validity. Remember we talked about that last time, that you have issue of the domain coming up in differential equation and the context of interval of validity. So let's see. So item number 1, this says initial values. So I have y is given to me as general solution, or one parameter. When we want to talk about a whole bunch of solutions, a possible solution, we talk about a family of solution. Means there are many that you can extract from that. One parameter refers to the fact that we have just this number floating here, C1. This is just a parameter. Any value you choose for C1 gives you some other solution. All of them fit this differential equation. Regardless of what C1 is, that's a solution of this. We want to select one of them. Just like when you are on a football court, you could start throwing ball at many places, and you can throw at various speeds and such. So that constitutes a family of solutions. Imagine all the balls up in the air. We want to select one of these guys. So here is our solution: 1 plus c1 exponential of minus x. So what does that initial condition mean? Initial condition means we are throwing the ball at x equal to 0 and y is equal to minus 1/4. Okay, so x equal to 0. Let me see if I can color this thing, and I'll probably have a problem that my background. This is my 0, and then of course I have my this is minus 1/4. Okay, now all I have to do is plug these numbers here. So I'll have y. So this thing sometimes is called x0 or y0, to 0 indicating when you get started. So I put y is equal to minus 1/4. Minus 1/4 is equal to 1 over 1 plus c1 exponential of, my x is 0. So this just becomes 1 over, of course, if you remember, exponential of 0 is just 1. 1 plus c1. So this denominator has to be minus 4. I have to have 1 plus c1 is equal to minus 4. Flip both sides. Of course, it tells you c1 is equal to minus 5, which tells you the solution that you have is 1 over 1 minus 5 exponential of minus x. So that's my solution. It says find a solution. Here's a solution that fits our bill that has this initial condition. Okay, I didn't leave enough room here for find the largest interval over which the solution is defined. You remember that we said these solutions that we have, they don't necessarily go on existing forever. Somewhere they might stop. Okay, let me first use a little software here that we are going to employ throughout the semester, and you are allowed to use it on the exams as well. It's the following, I guess, let me see. Sorry. So it's called Desmos. I'm sure you have used it. So the function I had was y is equal to 1 divided by 1 minus was it 5 exponential of minus x or something. Okay, it's some function. Okay, it's some function. Now we see a peculiar behavior in this function. It ruptures. It goes toward the minus infinity on this side, plus infinity on that side. It has a so-called vertical asymptotes. At some point, this function ruptures. You remember in the case of interval of validity, we said in pre-calculus, you have functions with their domain. So your domain is these two pieces here in differential equation. Depending on where you start, you pick one of the pieces. So in this case, we had our initial x, so that's 0. So that was where we started. So the left side is going to be our interval of validity. But how do we do this thing theoretically? how do we get to our number? So let's go back here. So what I do is that rupture is happening because I divide by 0. So I have, let me write here, 1 minus 5 exponential of minus x has been, you divide it by 0, and that's what caused all the problem. So let's rearrange this thing. So I have 1 is equal to 5 exponential of minus x. Multiply both sides by exponential. So exponential of x becomes equal to 5. Okay, this has to be 5, so the product is, so, and then x, how do we solve that? Okay, let's take a logarithm, x equal to logarithm of 5. That is where that vertical line was. That vertical line on that picture I showed you was at logarithm of 5. And since we are starting at 0, we have to stay to the left of this. So interval of validity starts from minus infinity, comes all the way to logarithm of 5. So interval of validity of the solution that we have. This solution that we have here is good for just this interval. We don't have, to borrow expression from Star Trek, we don't have a beam me up, may help me jump to the other side of the vertical asymptote and such. I am imprisoned to one side, and that's where I exist. Okay, the story is similar for higher order differential equations. Here is something, again, we are going to see this thing later on, a differential equation which is x double prime plus x equal to 0. Implication is that the independent variable is perhaps t, as you see indicated here. So x is a function of t. This is indicating an example of a simple oscillation, just like what we saw in first couple of videos. And it says find a solution of the second order initial value problem which satisfies x0 is equal to minus 1 and x prime 0 is equal to 3. So we have our x is given to us as c1 cosine of t plus c2 sine of t. And we are said that x0 is minus 1 and x prime 0 is equal to 3. This 0, this refers to the value of t. So this means x, t on the right hand side, it has to be replaced by 0. Okay, we need to remember some basic ideas from trigonometry. Of course, one of them is here. Sine of 0 is 0, cosine of 0 is 1, and over there we had another one of these things. Exponential of 0 was 1. So we are going to make use of these things. So this becomes c1, because this is 1, this is 0, and this is supposed to be minus 1. So straight out I get this. And then x prime, well, what is x prime? X prime is a derivative of this expression, so we need to remember derivative of sine and cosine. So it's going to be minus c1 sine of t plus c2 cosine of t. So x or x prime of 0, this is going to be minus c1 times sine of 0 plus c2 times cosine of 0, and again sine of 0 is 0, cosine of 0 is 1. This thing just boils down to c2, and that has to be x prime of 0, that is 3. So this problem solved to give us x is equal to c1, which is minus 1 times cosine of t, and then c2 is 3 sine of t. That is the solution of So let's get familiar with the terminology. Two-parameter family of solutions. Two-parameter refers to this C1 and C2. Of the second order because this is x double prime, differential equation, which is what we saw here. Another piece of terminology, initial value problem. At the very beginning, like at time 0 at certain time, these values are given. Most often initial time is set at 0. It's like you are calibrating things at 0, but doesn't have to be. Initial time can be any number. Okay, another question we are being asked here is just playing around with the differential equation, try to come up with some ideas. Here it says by inspection, so essentially that means anything goes. You're guessing as best as you can for a solution of an initial value problem. The point of this problem is saying that there are more than one. Okay, that's an exceptional situation. Most often throughout the rest of the course material, differential equations we come across have just a unique solution. We are not going to see many cases where there are more than one solution. That corresponds to our physical intuition that if you throw a ball, it's going to go in a certain definite path. It's not like the laws of physics are going to be one thing on one day and another thing going to be another day, and a ball that was expected to go forward perhaps will go backward. So we don't have those kind of strange phenomena in the physical world or the usual physical world, but certain mathematical expressions could show this weird behavior that you might have two outcomes in a situation. Okay, all of that discussion aside, how do we go about guessing here? So I'm taking derivative of some function and it becomes a different power of the same function. So what does that remind us of? Playing with the powers. Well, the easiest thing to go after is like perhaps we are just guessing. Y is some power of x. Well, I don't know what power of x, so I just write some power of x, x to the power of n. I don't know what n is that will work here. And perhaps it has a multiple. I don't know that one either. So we are starting with some guess, maybe a bad guess, maybe a good guess. We work it out. Okay, how do we check if this thing works at all? And if it does, well, what are these values? So we go back to the equation. It says we expect something from y prime, which is what? Well, y prime, the derivative of this thing is n a x to the power of n minus 1. What we expect this thing to be is supposed to be twice y to the power of 1/2, which is twice. Now what was y to begin with? A x to the power of n to the power of 1/2. So we remember that when we have a product raised to a power, I can take it and write it like this. A to the power of 1/2, x to the power of n to the power of 1/2 becomes like this. Well, now what? If this wants to be same as that, then the x portion has to match the x portion and the coefficient has to match the coefficient. Would that work? Well, let's see. If the x portion has to be matching, then x n minus 1 has to be same as x to the power of n over 2. That means the exponents have to be the same. Okay, I take n over 2 to the left. Excuse me. I take 1 to the other side. This tells me n over 2 is equal to 1, which tells me n is equal to 2. So far so good. What else do I expect? whatever was number in front of this thing has to match whatever was in front of that one. So NA has to be same as 2a to power of 1/2. Well, n was 2. Let's just replace that. 2a has to be 2a to power of 1/2. Well, 2's cancel from both sides. I have an equation. A is equal to a to power of 1/2. What is the solution of that? Well, let's bring both of these things to one side. A to power of 1/2, I can factor it. A to power of 1/2 minus 1 has to be 0. Product of two things is equal to 0. Another one of the basic facts from algebra we need to remember. If product is 0 of two things, either the first one is 0 or the second one 0, and rarely perhaps both of them are 0. It only works if the product is 0. So we cannot say if the product is 5, one of them has to be 5. We don't have that. It applies to 0. So either a to power of 1/2 is 0, which means a is 0, or a to power of 1/2 minus 1 is equal to 0, which means a is equal to 1. So I got two answers. One, a is equal to 0, which means y is 0 all the way. Or a is equal to 1. If a is equal to 1 and I got the n equal to 2, I have x to the power of 2. So I have two answers, two possible answers. So either y is 0 or y is equal to x squared. We said that is going to be a rarity in our problems that we're going to see later on. We don't usually see multiple solutions because differential equations are supposed to represent our physical world, our usual physical world, and things happen in just one way. There isn't any choice of option 1 or option 2. Okay. Next topic up, which we promised we are going to briefly mention and then move on, is the issue of boundary value problems. Boundary value problems, typically abbreviated like this. Well, again, let's go back to that playing a ball game, playing football. What are the main objective of one of the main objectives of the game is to pass the ball to somebody. So if you are here with the ball in your hand and you're passing it, and then you expect somebody to catch it, is that right? So it's not that you're just throwing a ball. You want something to happen at the end. So if you put a restriction at the beginning on a process and also at the end on that same process, you are talking about boundary. Boundaries refers to, here you have a beginning and here you have an end. So you have two different points you are considering in your whole process. You have a certain start and a certain end in view. So some of the questions you might come across might ask you, for example, to solve y double prime plus y is equal to 0, differential equation, and then it might tell you, well, at the beginning I want this thing to be 1, and at the end, and well, it depends on what a person considers to be an end. For example, pi seconds later, or whatever, how many seconds later, y at pi is going to be, say, a certain other number 2. So that would be an example of a boundary value problem. And just like the other problems, you can play with that and try to ascertain if you have a solutions, if you have one or two or many, and all sorts of questions related to that. We are just mentioning this thing, maybe solve a couple of problems related to that, but it is delegated to a future course on differential equation. We are not going to have enough time to deal with that extensively. Another topic that we are going to just briefly mention is the issue of existence and uniqueness. Anytime you solve a mathematics problem, you want to know, well, is there something to be found? That's the issue of existence. When you're trying to solve a problem and you're investigating for yourself, one of the fundamental questions to deal with is, well, is there anything to be found at all? Perhaps the equation you're looking at has no solution. The other issue is uniqueness. So suppose you find one solution, there's always a nagging concern that there can be another solution, or there can be a third one, and so on. How many of them are out there? So that's the issue of uniqueness. And there are other issues like if I change the initial values slightly, what happens to my function? That is the issue of dependence on initial data. Like how sensitive is this problem to how things get started? Those are more advanced issues. I just briefly mentioned something about it, but we have to postpone that as well, because probably it goes beyond the preparation that we have at this point. So we have a so-called theorem for existence and the uniqueness. It is in the context of giving an initial value problem. So we have a general statement. Y prime is given to us as some function of x and y, as we said before, and there is a initial point, y of x0 is equal to y0. So the question is, if there is any recipe out there that will give us a clear-cut picture of existence and uniqueness. Well, there are some general statements to be made, rather theoretical, but it runs like this. If you go and investigate based on the right-hand side of this equation, this f that you have, depending on how this f behaves, you can have something to say about existence uniqueness. First of all, if you can specify, well, there is an x0, y0, which where your initial data is at. If you can find some rectangle around this, okay, some rectangle around this thing, we are on the xy plane, on which f and its partial derivative with respect to y are continuous. So if y, if correct this. If f of x and y and partial of f with respect to y, this means taking derivative of f with respect to y. This is something that you see in calculus 3. If you are not familiar with it, don't worry, it just means differentiating with respect to y. If f and partial of f with respect to y are continuous on, let's call this thing rectangle R. If it's continuous on R, then there is a unique solution. Okay, we were trying to figure out if the solution exists. Unlike that problem we just solved, where there were two possibilities, there is a unique solution. However, how far does this unique solution lives? That's going to remain a little bit of a mystery. So it's going to interval of existence of this unique solution is only guaranteed to be some unspecified interval around your x0. So from a little bit to the left, we cannot even say how far is that little bit. From a little bit to the left of this to the little bit to the right of it, there is a unique solution. That's all we can say. So it's a rather vague statement that there will be a kind of unique solution, and it has a limited, at least we can guarantee that it exists on a certain interval, and that is all one can say. Now you can read more about it in the text, and otherwise you can postpone this issue to some time in the future. Okay, until next time, good luck and God bless.